Hello and welcome to my presentation. This is joint work with Mateusz, Kwaśnicki and Akaki Mamageishvili on axioms for constant function market makers. So first of all, what are constant function market makers? They are a simple class of mechanisms to trade financial assets. And originally, these kind of mechanisms have been introduced in the context of prediction markets. Actually, a lot of the early work on prediction market AMMs has been presented at EC. But more recently, for the last 4 or 5 years, they have been very popular in the context of cryptocurrency trading. So if you want to trade cryptocurrencies, you usually have two types of trading venues where you can do that. One are these called centralized exchanges, which usually operate in a conventional way. You have an order book exchange, and there is an intermediary who takes care of custody of assets and of settlement of trades and so on. And as an alternative to that, in the spirit of decentralization, you have so-called decentralized exchanges, DEXs, that use blockchains too for the purpose of trading. So the benefit of them is that users keep custody of their funds as themselves on the blockchain, and a smart contract on a blockchain implements a mechanism for trading and for settlement of the different cryptocurrencies. And the CFMMs are heavily used in this context for constructing decentralized exchanges. Why? Because computation is usually expensive if you want to run something on top of a blockchain. So you want to go for a simple design, and CFMMs provide a very simple design. But also, they tend to perform rather well in financial assets where you have little or not so much liquidity. So they perform rather well there. To give you a sense of magnitude, about around 10% of total cryptocurrency trading happens in these decentralized exchanges, usually cleared through a constant function market maker. Last year, there was an average of $3.4 billion US of trading volume in these kind of markets. So significant amount of trading volume. It's a bit less now because of the depreciation of the value of cryptocurrencies, but still very significant. So they're worthwhile studying these kind of mechanisms. So how does it work? The trading infrastructure is usually one of trading against a pool of liquidity. There are two kinds of users in these protocols. You have liquidity providers who provide liquidity, for example, in a token pair or in a pool of several tokens. So they bring different amounts of the different tokens to this constant function market maker. And that constant function market maker uses this liquidity, pooled liquidity by different liquidity providers, to make a market. And so traders interact with these CFMMs by trading against the pool. Now here's the constant function part of this thing. The market is usually made in such a way that, abstracting away from trading fees, some function of inventories of the different tokens that are in the liquidity pool is kept constant. So to give you one example, the most popular example of this kind of constant function market makers, let's look at the constant product market maker, which was the original market maker of the Uniswap protocol, the most popular of these decentralized exchanges. For the case of two tokens, the constant product market maker works as follows. So liquidity providers bring tokens A, token B, and there's some inventories of those. Inventory of token A, IA, and inventory of token B, IB. And now somebody wants to swap against that pool of liquidity. He brings X amount of type A tokens, and we're wondering, how many type B tokens Y would he get? And to determine that, we use a product as an invariant. So we compare the product of inventory pre-trade, which is IA times IB, and post-trade, which is IA plus X times IB minus Y. And that implicitly defines, if you set those two quantities equal, it implicitly defines you an amount Y that the trader gets in exchange. So you always maintain the product as an invariant. And now, natural question is, of course, why would you want to use a product? Why don't you use a different function? Can we think systematically about different functions for these CFMMs? And can we think about economic design of those so-called liquidity curves? And this is what we're doing in this paper. And there are different angles that you can take. We take an axiomatic approach, which is particularly useful if you have sort of a huge design space and many different choices that you could make. Axiomatic approach introduces desirable axioms or properties of these invariant functions, trading functions, we call them. And a combination of those natural intuitive axioms leads to a restriction of the class of feasible trading function. And what we do is we get a very nice parameterized class of trading function by a combination of what I think are very intuitive axioms. So that's our main contribution. And the constant product market maker is one of the market makers in the class that we characterize. And it's sort of an extremal point in this class. It's the least convex of those trading functions. It's trade optimal. So we give some kind of normative justification for the constant product market maker. As a bonus, we also get an axiomatic characterization of a popular class of AMMs used in prediction markets, logarithmic market squaring rules, where we just use the same kind of axiomatic approach and just replace one axiom, an invariance axiom, by another one, and then we very naturally get a characterization of these functions. Okay, here's a setup. It's a very simple setup. We have a finite set of asset types, so some tokens, cryptocurrencies you can think of. A token A, a token B, a token C, depending on how many assets are traded with this AMM. And the fundamental object to make a market is a trading function. A trading function assigns to each vector of inventories of the different assets. So the pool liquidity defines inventories for the different assets. It assigns to each such inventory vector a number, a real number. And you can sometimes give that number an interpretation. So you could interpret it, for example, as a value of the inventory vector measured in some appropriate numeric. So we make a mild assumption on the trading function that's supposed to always hold. They should be strictly increasing and they should be continuous. Otherwise, we don't make any other assumption. But of course, we will impose some axioms and they will restrict the class further. Now, that defines your market because now people can trade against this trading function with this trading function. And they do so by executing trades, which leads to a change in the inventory. So a change in the inventory a vector. And usually in this decentralized exchange, at least we think of two types of trades. We think about swapping tokens for another. I already explained to you how this would look like. But also we can think of another kind of trades that people can make. They can act as liquidity providers in this marketplace. And they could add liquidity to the pool. And that's basically adds proportionally to the inventory vector. That's a trade. Or if they have already provided liquidity, they might want to remove it. And so then you remove proportionally from the inventory. So that's another kind of trade that you can do. So to do the latter kind of operation, usually what is happening in these decentralized exchanges is if you bring liquidity, you get a token in return that is you can interpret as a tokenization of a share of the pooled liquidity. So you can claim ownership of a share of the pooled liquidity. And for example, you can use that to have a claim on the trading fees accumulated by the same. So a natural interpretation of the numeraire in this context in the decentralized exchanges, you can think of it as a tokenized version of a share of the pooled liquidity. Usually it's called an LP token, liquidity provider token. Okay. So that's the setup. And now we want to make sense of different properties that such function should satisfy. So let me give two examples, because they are very popular examples in practice of such trading functions. So one is a generalization of the constant product market maker, where you take a weighted geometric mean of the different inventories. So you could have weights instead of just having the same power on all of the terms of the product. So that's something used, for example, by Balancer, which is third or fourth most popular trading venue in terms of decentralized exchanges. Another one I wanted to introduce because, first of all, it's the second most popular AMM, and also it's a convenient counterexample for many of the axioms later on, is this curve market maker, which has this rather complicated invariant function that is implicitly only defined. But one feature of it is that the liquidity curve or surface defined by it is sort of flat towards the middle. You almost have constant exchange rates, and towards the ends it's very steep. So it's used for trading assets are supposed to be highly correlated in value to each other. For example, different stable coins. So one more piece of definition, and then I want to go into axioms. So we introduce a notion of equivalence, which is very natural for these trading functions. So if you only care about the terms of trade offered by this CFMM, then it doesn't really matter how you measure the liquidity, which numbers you assign to this inventories. All that matters is that you have defined the liquidity surfaces or the liquidity curves. So all of the curves that lie on a level curve of this function. And in particular, it shouldn't matter that you apply monotonic transformation to a trading function, which still makes a market in a similar way. You just measure liquidity differently. So there is a national notion of equivalence classes up to monotonic transformation. The other piece of notation I wanted to introduce is the marginal exchange rate that is defined whenever we have differentiability of the trading function. Then you can define a marginal exchange rate. It's just a slope to the curve for the surface. Now, axioms. And here is the main driver of all of our results, the most important axiom for our characterization, which is independence, or which you can also interpret as a separability condition. And that has the feature that it restricts trade among how trade among a subset of assets reacts to changes in inventory of non-traded assets. Only has bite if you have more than 2 assets in your pool. But in this case, it says the exchange rate, for example, between 2 assets shouldn't depend on the inventory of assets that are not included in this pair. Right? So the exchange rate between A and B token shouldn't depend on the inventory of C tokens I have in the A. More generally, if I trade between token A, B, and C, the terms of trade that I have there shouldn't depend on the inventory of token D. So to go back to our 2 examples, the geometric means that I've introduced, they are independent by definition because they just give you proportionality between the exchange rate and the ratio of the inventories of the 2 tokens. So there you have independence. The curve rule I've also introduced violates independence. Why? Because the exchange rate between a token A and a token B happens to be influenced by the inventory of the 3rd token C in the pool. If you do the math, this is your exchange rate, and yeah, there you have a dependency on a non-traded asset. Okay. So independence is the first axiom. Now there are 2 additional axioms which are much milder than independence, but they allow us to pinpoint a nice class. And the first one is scale invariance, and that has to do now not with terms of trade, but rather with how the AMM reacts to the addition or removal of liquidity. So if you add liquidity to the pool proportionally, this axiom tells you that the marginal exchange rate shouldn't change as a reaction to that. Could be that the terms of trade react to a change in liquidity, of course, right? If there's more liquidity in the pool, then trading should lead to less price impact. But at the margin, the exchange rate shouldn't change. And that's scale invariance. The third piece, or the third axiom that allows us to get a nice classification is a sufficient funds axiom, which tells us that we should never run out of liquidity. Okay. So here's the axiom. You start trading in some inventory vector. You start at some inventory vector, and then you start trading along a surface or curve. Then after executing your trade, you still, if you started with positive amounts of each of the assets in the inventory, you should still have positive amounts of each asset in the inventory. Okay. So in other words, the AMM always makes a market. Exchange rate might be very bad that you can get if the AMM runs out of one asset, but it never completely runs out of one asset. So you're always able to make a trade in principle. Geometrically, it means that liquidity curves or surfaces do not intersect with the axis. Okay. And again, all of the examples previously, they satisfy this axiom. Okay. What do you get if you have these 3 axioms: independent, scale invariance, and sufficient funds? One idea is to generalize this idea of a geometric average. I told you that there the exchange rate between 2 tokens at a particular inventory vector, the marginal exchange rate, is equal to the inventory ratio. And you can generalize it in the following way. You have that the marginal exchange rate is equal to some power of the inventory ratio. And if you do that, you get a class of functions that generalize products or geometric averages. Okay? You get these kind of constant inventory elasticity market makers. Okay, so CES function, so to speak. Okay, and now the interesting thing is that this basically gives you the class. Let me be bit more precise. So in the previous formula, you can also introduce coefficients to deal with asymmetries in the different assets. So you can add coefficients in front of the monomials, and or in the product, you could add coefficients in the exponent. But that defines you a class of functions, a well-parameterized class of functions. And they are, by construction, it's easy to show that they are by construction scale invariant and independent. And the third axiom, sufficient funds, gives you a further restriction that this M factor by which you look at the proportionality between the margin exchange rate and the inventory ratio has to be greater or equal to 1. And that's it. That's the class, actually. So if you have independence and scale invariance and sufficient funds, then your trading function that satisfies those things, axioms, is necessarily equivalent to a constant elasticity market maker, where this parameter in the formula is M greater or equal to 1. Okay. I cannot show you the proof because for the interest of time, but it relies on some classical results from decision theory by De Broglie, where independence gives you a separability condition on preferences, and it allows you to write your trading function up to monotonic transformation in an additive way. And then you can show that if you combine it with other axioms, that you have that the different one-dimensional functions, additive representation, have a power form or logarithm form. A couple of remarks. Result is not true for the two-dimensional case, and we have results on the two-dimensional case in the paper. But independence has no bite in the two-dimensional case, so it would be true in two-dimensional. We need another axiom in that case. We need continuity, but no differentiability assumption is made, and also no convexity assumption in principle is made by us. So one nice thing and one nice technical contribution is that you can show these things even if you don't have differentiability. And differentiability is implied by the other axioms. Okay? And also convexity is implied by the other axioms. If the sufficient funds axiom would be dropped, then we still get this particular functional form, but now you don't have any restriction on the M parameter. However, if you were to replace it by, for example, quasi-concavity, which is a very natural axiom, then you would get a restriction of the kind M has to be greater or equal than 0. Final remark on these things here is you get also, you can rank these constant elasticity market makers by convexity. That is straightforward if you assume symmetry on top. And what you could get as sort of a normative justification, and that's an easy result actually, as a normative justification of constant product rules, is that it is extremal if you rank trading functions by convexity within this class of scale invariant, independent, symmetric, and sufficiently funded AMMs. The final thing I wanted to show you is a nice connection to prediction markets. So prediction markets look a bit different, the kind of market infrastructure that you have there. And one particular difference is that the kind of assets that are usually traded in prediction markets. These are arrow de Broglie securities, which means that they have a binary payoff. So they either pay 1 if you match the state of the world, or they pay 0 if you don't match the state of the world. And so you can bet on different outcomes. And if you get it right, you get one unit of numeraire. Now, if all of those arrow de Broglie securities span basically all possible outcomes the world has, then in particular, if you buy one of each arrow de Broglie security, you have a perfectly hedged portfolio that pay 1 unit out regardless of the state of the world. And so a fair value of buying such a portfolio should also be 1 unit of numeraire. Okay, so that's why a prediction market AMMs usually satisfy translation invariance. So why am I telling you that? Because here's a nice connection. If you replace the scale invariance property now by this translation invariance property, then we get a characterization of a different class of function, which have been very focal in the discussion of prediction market AMMs, so-called logarithmic market scoring rules, which take this form of the log of a sum of exponentials. Okay. And it's rather easy to see. It's a change of variables arguments that if you if you replace scale invariance by translation invariance in our previous characterization, you get the logarithmic market scoring rules. And constant sum market makers I also have to throw in because that's the limit as B goes to infinity. So to conclude, we have introduced an axiomatic approach for AMMs, for DeFi, which I think is a very natural approach for economic design. Very simple combinations of axioms of basically a separability condition and a homogeneity condition give meaningful restriction on the viable trading function. And not only that, but also we could optimize over this class, and the constant product market maker was an extremal point in this class. And then if you replace the invariance property by another invariance property that is natural in prediction markets, we got another nice axiomatization result for the logarithmic market scoring rules. For future research, what seems to be an interesting direction is this entire discussion of fees, which we abstracted away from. And of course, also to think beyond independence. Can we replace it by something milder? Separability sometimes makes a lot of sense. Sometimes if you have correlation between the assets, then maybe not. And we would be interested in to have also meaningful characterization results without the independence maximum.